In this video, we are going to look at some of the differences between ionic and covalent bonds in terms of polarity, and we're also going to look at something called intermolecular forces. So when we look at ionic bonds and covalent bonds, when they join together two atoms, they're very rarely purely ionic or purely covalent. So there's a little bit of overlap. So when we look at this, we call it bond polarity. And when we look at bond polarity, we have to analyze the electronegativity of the different atoms involved in the bond. And so as a refresher, electronegativity is the ability of an atom to attract electrons within a compound. So the higher the electronegativity, the more likely the electrons are to be found by that atom. So high electronegativity equals attracting electrons. Low electron negativity equals not attracting the electrons. So when we look at this chart, the numbers now are telling you that element's electronegativity. So fluorine is the most electronegative element with 3.98, and so it is most likely to attract the electrons versus like lithium, whose electronegativity is only 0.98, so it's likely to not have the electrons. So the degree to which a bond is ionic or covalent can be calculated by subtracting the electronegativities of the elements in the compound. So for example, if we looked up potassium's electronegativity in the chart, which is a 0.82, and then let's say it bonds to fluorine, and we said fluorine was 3.98. If we subtract those two, and when you do the subtraction, always do it so you get a positive number. We do 3.98 minus 0.82 and come up with a difference in electronegativity of 3.16. And so when we do that, we can look up this difference at 3.16 on this chart. And so here we have compounds are mostly ionic when their difference in electronegativity is 1.7 or higher. They're mostly polar covalent bonds when the difference in electronegativity is between 0.4 and 1.7. And then they're mostly covalent when the difference in electronegativity is less than 0.4. So in this particular example, we have an ionic bond because our difference in electronegativity is higher than 1.7. And so a nonpolar covalent bond is a covalent bond in which the bonding electrons are shared equally between the two atoms. So the distribution of electrical charge is balanced between the two atoms. The molecule will look symmetrical. This happens with our diatomic molecules like H2, N2, O2, etc. They have an even distribution of their electrons, and so they produce a very symmetrical molecule. Polar covalent bonds is a covalent bond in which atoms have an unequal attraction for the electrons, so the sharing is unequal, and the molecule will be asymmetrical. And we'll look at some pictures of these in a little bit. Sometimes these polar covalent bonds are simply called polar bonds. And back up to this nonpolar, you don't have to have diatomic molecules in order to have nonpolar bonds. There are other compounds out there that are different elements and not diatomic molecules. So it doesn't have to be a diatomic molecule in order to have a nonpolar covalent bond. It's just they are definitely likely to have a nonpolar bond. So when we look at these pictures, our nonpolar covalent bonds, in this case we actually have the diatomic molecule of chlorine. Both of them have electronegativities of 3. When you subtract them, we get a difference of 0, which puts us as a nonpolar covalent bond. And you'll see here that this molecule is very symmetrical. We could draw a line down the middle and it's mirrored image on both sides. However, when we have hydrogen fluoride, we now have a polar molecule, and we can see if we looked at their electronegativities, fluorine is 3.98 and I believe hydrogen is 2 point something. And so we draw these Greek letters, they're called deltas, and we read this whole situation as partially positive, and this side would be read as partially negative. And when we look at the electronegativities, we see that fluorine has that higher electronegativity. So the electrons of this whole compound are more likely to be found floating around the fluorine atom versus the hydrogen atom. So those electrons are pulled to the fluorine atom, giving pretty much just this hydrogen atom the positive charge, and that fluorine atom will have a slightly negative charge to it because of that extra hydrogen electron being incorporated into that orbital. So that gives the fluorine side over here a bit of a bulge to it because it's got that extra electron, and the hydrogen side is a bit decreased. And so now if you were to draw a line down the middle here, we don't have mirror images on either side. They're not the same. Another way to write this, that the fluorine has that partially negative, is to draw an arrow here above the symbols pointing to the more electronegative element, and then this crossbar right here is indicating a plus sign over the hydrogen, saying that that hydrogen is partially positive. So that's kind of a look at the asymmetry and the symmetricalness of nonpolar and polar covalent bonds. So to practice, we have a couple examples. Which type of bond will form between each of the following atoms? And so in order to do this, you do need this electronegative chart. So for the first one, we can look up carbon. Carbon has an electronegativity of 2.55. And oxygen has the electronegativity of 3.44. Again, I'm getting these off this electronegativity chart. And so in order to figure out what type of bond, you simply subtract them. 3.44 minus 2.55. And remember, do it in a way that your answer is positive, 0.89. And then you can go back and look it up in that chart. Anything greater than 1.7 is ionic. Between 0.4 and 1.7, I don't know if that's the right symbol, is nonpolar. And anything less than 0.4 is polar. So in this particular case, 0.89 falls in between 0.4 and 1.7, so this would be a polar bond. Next example, sodium's electronegativity is 0.93 and nitrogen is 3.04. Again, set up the subtraction, which I'm assuming you would just do on a calculator, by the way. I'm just showing this step so you can learn the process. And so in this case, the differences in electronegativities is 2.11, which is greater than 1.7, which gives us an ionic bond. And lastly, we have boron and hydrogen. Boron's electronegativity is 2.04 and hydrogen's is 2.20. So when we do the subtraction, we get a difference of 0.16, which is less than the 0.4. So we have a nonpolar structures. Sorry, it is. I goofed up here, guys. This would be. They had them switched around. Polar and nonpolar. Sorry about that. And so down here we would have a nonpolar bond. All right, so a polar molecule is a molecule in which one end of the molecule has that slightly positive charge and the other has slightly negative. And we call this a dipole. Di meaning two, and we have two poles, one being positive, one being negative, kind of like a magnet. When we have an unpolarized material, we have the atoms or the molecules floating around with their positive and negative ends kind of just randomly distributed. When we polarize that material, we apply an electric field to it so that one side of the electric field has the positives and one side has the negatives. So then the atoms or the molecules in that compound align so that the negative ends of the molecules are pointing to the positive side of the electrical field, and the positive ends of the molecules are pointing to the negatives, because remember, opposites attract. And so when you have polarized sunglasses or lenses, this is the atoms or molecules of those lenses have been polarized, so they've been exposed to that electric field, and so the molecules have lined up, which allows us to see a little crisper images. So the molecular geometry of a molecule affects its polarity. So when we look at these structures, we have carbon dioxide here, and when we look at their electronegativity, we see that oxygen is the more electronegative atom of the compound, and so from carbon, some of the electrons are going to be pulled towards the left oxygen, and some of the electrons are going to be pulled towards the oxygen on the right, leaving carbon with that partially positive charge. And so this creates a dipole situation where the oxygen sides are positive and that middle is the oxygens are negative, and that center carbon is partially positive. Here with the water molecule, because of these lone pairs of electrons and oxygen having a higher electronegativity, the electrons are being drawn up towards the oxygen atoms, leaving the hydrogens with the partially positive charge, and oxygen will be partially negative. So we have a negative charge up by the oxygens, giving two kind of polar fields if you looked at each half of this atom, so that the negative is by the oxygens and the positive is by the hydrogens. So both of these examples exhibit dipoles. When we look at a couple more examples, we can see hydrogen and chlorine would have a dipole effect because and creates a polar molecule because the hydrogen atom is less electronegative than chlorine, so the electrons are being drawn towards the chlorine. This is happening in all of these examples, is that the electrons are being drawn to one specific atom. And so this creates a polar charge. So where the arrow is pointing is going to be that partially negative atom, whereas everything else, I believe they're in the whitish gray, are going to be partially positive. Nonpolar molecules have an equal pull from those electrons. So in this boron trifluoride, you can see that all the fluorine atoms are going to be partially negative, while this center one will be partially positive. And so because of this, we have a bit of symmetry. If we were to draw a line down the middle, there's some symmetry as to those electron distribution. Same here with this carbon tetrachloride. We have that symmetry going on, and that it's almost like this pull of the electrons this way cancels out with the pull of the electrons downward, in the same way crossways. The pulls of the electrons are getting canceled out because they're pointing in opposite directions. Whereas in all of these examples, the electrons are all pointing the same way, so they're not getting canceled out. So the next topic of this video that we're going to look at is something called intermolecular forces. Up until this point, we've been talking about intramolecular forces. Those are the forces that hold a molecule, like one single molecule, together. Intermolecular forces occur between multiple molecules. And so these are the molecules that hold other molecules together. These are weaker than either ionic or covalent bonds. So we have van der Waals forces, and these are the weakest intermolecular force, and they consist of two types. We can either have dipole-dipole forces, or they call them London, after the guy who discovered them, London dispersion forces. So a dipole-dipole force is the attractive force that occurs between polar molecules, and this is the attraction of the partially positive or partially negative end of one molecule to the partially positive or negative side of the other molecule. So we draw this with the dashed lines here, indicating that because the chlorine is partially negative, there's some attraction to this partially positive hydrogen part of another molecule. So the molecules will align themselves so that the oppositely charged regions of neighboring molecules are near each other. And that makes sense because we know that these like charges, let me redraw that. The like charges are going to want to repel one another. And so these guys will play nice and kind of bond together. It's not a very strong bond, it's just an interaction that says you have a positive charge, I have a negative charge, let's kind of be friends. Your London dispersion forces are intermolecular forces that occur between all atoms and molecules due to the random motion of electrons. So in the electron cloud of a helium atom, there's two electrons. And so when averaged over time, these electrons will distribute themselves evenly around the nucleus. However, at any given instant, that electron distribution may be uneven, resulting in an instantaneous dipole. And it only lasts for a brief second because those electrons are constantly moving. So the strength of the dispersion force increases as the total number of electrons in the atom or nonpolar molecules increases. So the more electrons, especially valence electrons, the stronger that London dispersion force will be. And so here's your instantaneous uneven distribution of electrons. So we've got those electrons mostly over here. We can tell that because it's partially negative, versus over here it's a little lighter color in the green. And we've got partially positive. One, the nucleus is located there, and the electrons are not. And so in a nonpolar helium atom, if we averaged out over time, we would see that those electrons, their average locations, give a nice nonpolar atom. However, at any given instance, that could not be true. So when we look at these London dispersion forces and the number of electrons, we can see evidence of the strength of these London dispersion forces when we look at the melting and boiling points, especially in the halogen family. So when we look at the total number of electrons, we can see fluorine has the fewest, iodine has the most electrons. And so when we look at their boiling points, we can see that iodine has a boiling point of 184 degrees Celsius, whereas fluorine with only 18 electrons has a very low boiling point at negative 188 degrees Celsius. So we can figure out that iodine has the greatest or strongest dispersion forces because it has the greatest number of electrons. It has the most electrons, so it's going to have the strongest dispersion forces. And so generally speaking, you can maybe assume that when a substance is a solid at room temperature, it's going to have fairly strong dispersion forces. The next intermolecular interaction that we have is something called hydrogen bonding. This is when we have a hydrogen atom that is covalently bonded to a small but highly electronegative atom, and it gets attracted to a lone pair of electrons of an atom in a neighboring molecule. This is actually very strong, however still weaker than an ionic or covalent bond. And this only occurs when hydrogen is bonded to either fluorine, oxygen, or nitrogen. And this is due to the three of these, they have a high electronegativity. So we can see in a water molecule, we know that water has those lone pair of electrons on the oxygen. And so that increases its polarity, its negative charge there. And so it's going to want to hydrogen bond or interact with this hydrogen partially positive of another water molecule. And so this hydrogen bonding, this will only happen if this atom right here is either oxygen, fluorine, or nitrogen. It will not happen with any other atoms in that position. And so this hydrogen bonding happens in water a lot, all the time actually. And so it gives water some special properties and makes water pretty cool, I guess you could say. So in the liquid state, those hydrogen bonds break down and reform as molecules flow from one place to another. So remember, those hydrogen bonds, they're strong, but they're not that strong. And so in the liquid form, it's really what allows water to be able to flow. Those hydrogen bonds will break and reform constantly. So when you pour a glass of water or water out of a water bottle into a cup, those hydrogen bonds are breaking and reforming, and that's what allows the water to move from the water bottle into the cup. So when water is cooled, those molecules begin to slow down and will eventually freeze, and it locks those hydrogen bonds into place, making it very frigid. And we'll look at an image of this on the next slide. The next thing is that bent molecular geometry of water will create gaps in the hydrogen bonding of network. Again, we'll look at that on the next page. That makes it less dense than liquid water, which is very unusual to have a solid that is less dense than its liquid counterpart. That means that solid water or ice floats on liquid water, which is very uncommon. So when we look at the structure of an ice cube, the red molecules or the red spheres are oxygen, and the little white ones are the hydrogens. And so we can see that these dashes, maybe I'll change colors here. These dashes right here represent the hydrogen bonds. And when water freezes, those hydrogen bonds get locked into place. And you can see that it's a gap. It really is a gap between the positive and negatives, which is kind of like, we could think of it as an air pocket, and so, or a space of emptiness. And so that allows, those molecules aren't jam-packed together, which makes it less dense, and so which allows it to float. So last thing we're kind of going to look at here is the boiling points and the bond types. So if a substance is in the gas phase, the particles must overcome the intermolecular forces holding them together. So this right here is your strength chart. London dispersions are less strong than dipole-dipole, and dipole-dipole are weaker than hydrogen bonding. So this is a weak to strong chart. So if the mass of the nonpolar molecule is large enough, its dispersion forces can be stronger than the dipole-dipole forces in lighter molecules. So this chart gives you a couple molecules, and it tells you or shows you the strongest intermolecular force at play. So in hydrogen, the dispersion, and when it says dispersion, it's really the London dispersion. It's the same thing, they're just taking a shorthand. So when we look at that, we can see their boiling points are very, very low because they have the weakest intermolecular forces holding them together. Then we go to the mid-range, this this dipole-dipole, and we can see that its boiling point has risen a little bit. And then overall, when we look at our next one, the strongest, the hydrogen bond, we can see that now we have the highest of the boiling points because hydrogen bonding is now being introduced and needing to be overcome in order to break apart those molecules. So molecular and ionic compounds, their physical state and physical properties of a compound will largely depend on the type of bonding that they have. So this chart gives you a nice comparison of ionic and molecular compounds. And so it tells you the type of elements involved in each, the type of bonding, the representative unit, the physical state at room temperature, solubility in water, melting and boiling temperatures, and ability to conduct electricity. So this chart is really a summary of probably the last couple, 2-3 chapters. So as a refresher, ionic compounds are between metals and nonmetals, where molecular compounds only have nonmetals in them. Ionic bonds transfer electrons. Covalent bonds share electrons. Your formula units are for ionic compounds. Remember the FUs. And the single unit of a covalent compound is a molecule. At room temperature, ionic compounds are solid, whereas molecular compounds can be solid, liquids, and gases. Ionic compounds have a high solubility in water, meaning they're likely to be dissolved in water, whereas molecular compounds could be dissolved in water or might not be. Melting and boiling points of ionic compounds are usually the higher, where molecular compounds will have low melting and boiling points. Ionic compounds will have a good electroconductivity if they are in solution or in the liquid form, whereas molecular compounds do not conduct electricity very well. So, like I said, this chart is a good comparison between ionic and molecular compounds, and we looked at using electronegativities in order to determine the type of bond that two elements will form. And we've now looked at intermolecular forces as well.